All right, welcome back to Introductory Physics. This is day 13, so congrats on making it more than halfway through the course. So we had a couple last things to finish up in chapter 5 before we move on to chapter 6 and start talking about energy. There were a couple of questions that you guys had at the end of last week, one about air resistance and one about how to deal with things on angles, like when we have a block sitting on a ramp or something like that. How do we analyze the forces in that case? So we're going to do both of those today, one example on a ramp and then just kind of a quick slide about air resistance, because it's not something that you'll see very much of in Physics 1, but I still want you to have that, at least an introduction to it, so you can start thinking through those equations in case your professor does decide to do a little bit of it. So here we go. All right, I want to start off with some give it a try questions before we do the actual calculations in this example, just to kind of review what we had talked about last week in applying Newton's laws. So here we have a car on a ramp or on a hill, and the car is in neutral as it rolls down this hill that's inclined at 20 degrees. So take a quick second, think through this situation. What are the forces that are acting on this car? Gravity is definitely one of the forces. Good, Gabriel. Friction, okay. And Colby coming in with the normal force. Yes, are there any other forces that are acting on this? Air resistance, okay, that's true. We'll kind of lump that in with friction for this example, since I haven't taught you yet how to calculate air resistance. Okay, well, that's great. Yeah, there are really those three forces that we're going to be thinking about. So gravity and friction and the normal force. Those are the three that we're going to be most concerned with. Why is there not like an applied force from the car? Right, Colby, it's in neutral. So we are not actually applying a force. Well, we don't know that there's no acceleration. We just know that it's in neutral, right? So our engine is not like actively pushing the car forward. Okay. So there we go, gravity, normal force, and friction. Next, I want you to draw a sketch of the free body diagram. What would a free body diagram look like for this scenario? Take a minute, sketch it out either mentally or actually on a piece of paper. Okie dokie. So there are actually a couple of different possible answers that you could choose for this free body diagram. And that's why I really wanted to go through this example with you today to show you the differences between those two options that you could choose. So really it depends on how you're choosing your coordinate system. Typically we've been working with a coordinate system like this, where we have positive y pointing straight up and positive x pointing to the right. That's one option. But you could also do it with your coordinate system rotated like this, where positive y is perpendicular to our hill and positive x points downward along our hill surface. And I would argue that in this case, it's actually much more convenient mathematically to do the rotated coordinate system. And I'll show you why using our free body diagrams. So in the first case, if we leave positive y being straight up and positive x being to the right, this is what our free body diagram would look like. Okay, we have the force of gravity pulling straight down. The normal force, remember, normal means perpendicular. So our normal force is going to be perpendicular to our surface at a 20-degree angle from straight up and down. And our friction force opposes the direction of motion. So this car is going to tend to roll down the hill, which means friction would be pointing up the hill parallel to the surface, so also at a 20-degree angle. So in this case, we have two forces that are on angles, and when we do the math, we would have to break down two vectors into their components as we think through the problem. Or if we use the rotated coordinate system, then we have the normal force, which is pointing straight up, because that would be perpendicular to our surface, is how we've chosen the positive y-axis. And in that case, our friction force, which is parallel to the surface, would be pointing in the negative x direction. And now gravity would be the one at an angle, a 20-degree angle. So you can see, like, visualize from the first free body diagram to the second, all we did is just kind of like rotated it a smidge. Well, we rotated it 20 degrees. So we wanted the most amount of forces to be on the axes as possible, right? So our normal force goes from a 20-degree angle to right on our axis. The friction force goes from a 20-degree angle to right on our axis. And our gravity goes from being right on our axis to a 20-degree angle. So we just take it and rotate it a little bit. Or you can just like turn your head and imagine it that way, if that makes more sense. But in this case, we just have the one force on an angle. So we just have one force that we have to break down into the component vectors. Okay, any questions about how to visualize those axes, why we would choose one coordinate system over another? Okay, I'm seeing some all goods. Let's keep going then, and I'm going to keep going with the rotated coordinate system, where the normal force and friction are on the axes, and the force of gravity is the one that's off on an angle, because I like simpler math. So another question that I want you to think through before we set up our equations: what is the car's acceleration in the y direction? What do you guys think? What is the car's acceleration in the y direction? Have a guess of negative g. Do we agree or disagree? Have a less than 0, so a negative. Okay, interesting, interesting. Well, again, I'm thinking from the mindset of this rotated coordinate system, and in the y direction, is our car being launched into the air or falling through the ramp if we choose this rotated coordinate frame? Hopefully not. It's not either of those, which means our y acceleration is 0 if we use the more convenient axes. Right, so if we just like rotate our head, then our car is not moving up or down. It's just moving to the side being down the ramp. But we don't have a y direction acceleration because it's not going up or down in that coordinate system. So that's another reason why this rotated one is a little bit more convenient to use for the math, because our y acceleration is 0. Oh, got it, got it. Okay. So now let's do some calculations with this. If the car is 1,000 kilograms and the coefficient of friction between the tires and the ramp is 0.45, what is the car's acceleration? So again, we already know it's going to have a 0 y acceleration, but it will have an x acceleration. It will roll down the ramp. I don't know if you guys live in hilly areas. Florida is like really flat. The only hills are causeways or like bridges. But if you live in a really hilly place, and you put your car in neutral, it's eventually going to start rolling down the hill. So there will be an acceleration, um, even though we're not forcing the car forward. It's just in neutral. So think about the y direction first, because we know the acceleration in the y direction should be 0. The sum of the forces in the y direction, we have the normal force pointing up. We have that y component of gravity pointing down. And in this case, the y component of gravity is this side that's adjacent to our angle. So the y component in this case is the cosine, which is super annoying because previously the y component was the sine, and here it's the cosine. So this is another one of those cases where, like, I always recommend that you draw a picture before you start trying to solve the problem. And for sure, draw a free body diagram first, because we can't just assume that it's the sine of our angle. It's not the sine of our angle, it's the cosine of our angle. It's the side of the triangle that's adjacent to our angle. Super annoying. But that's how the cookie crumbles. So since we know our acceleration in the y direction is 0, that means we can set the normal force equal to that y component of gravity. So normal force equals mg cosine of theta, where mass is 1,000 kilograms, g is 9.8 meters per second squared, and our angle is 20 degrees. So once we do all the number crunching in our calculator, we get a normal force of 9,209 newtons. Are we done? No, I wish we were, but we're not, because the question did not ask us for what is the normal force. It asked us, what is the car's acceleration? But you'll find that you need the normal force in order to find the acceleration. So we can't skip this step, really. So there's our answer from the previous slide up there in gray. Now we're going to look at our x direction. So the sum of our forces in the x direction is our x component of gravity minus our force of friction equals mass times acceleration in the x direction. So our x component of friction is, in this case, the sine of our angle. Again, super annoying because previously the x component was the cosine, and now that's just not true based on how we established our coordinate system. But we still calculate the force of friction the same way. It's mu, that coefficient, times the normal force. Aha, that's why we needed the normal force. So once we plug in our numbers, 1,000 kilograms times 9.8 meters per second squared times the sine of our angle, that gives us the x component of gravity. The friction force is our coefficient, 0.45, times the normal force that we just found, 9,209. And then again, our mass is still 1,000 kilograms. All we have left to do is simplify that and solve for the acceleration. And we find that the acceleration is negative 0.79 meters per second squared. Okay, so this acceleration tends downward. Okay, do you guys have any questions, comments, concerns about this example, dealing with rotated coordinate systems, etc.? Okie dokie, I'm not seeing any questions. Ooh, that one. If we use the other graph, the sine and cosine would be used in the same way as before. No. Let me go back to that picture. Okay, so if we were dealing with our x components, we'd still have, like, the x component of the normal force is still the side that's opposite our angle, which is the sine, for our normal force. For our friction force, the y component would be sine, which is just super annoying. It's just because of way that we draw our free body diagrams, the way that we establish a coordinate system, either way, you're going to have an x component that's a sine and a y component that's a cosine. But here in this one, we have our y component that's the sine and the x component that's the cosine, like we're used to seeing. It's just super annoying when you're dealing with things on ramps like this. So that's why you just have to be um, aware of what you're doing. You have to pay attention. Don't go through these problems on autopilot. Make sure you draw a picture, and the picture will give you that clue as to what to do. Okay, yeah, should be good after some practice. For sure, I recommend practicing some of these. I'll put up some more practice problems on Canvas. I meant to do that this weekend and it just totally slipped my mind. But I will do that. I'll put up some resources for you on Canvas today to kind of wrap up chapter 5, these types of calculations. Another question, where did mass come from in m sine theta? Let me get back to our slide. Okay, is this the one that you're referring to, Marco? Yes. So when we're thinking about the x components of all of our forces, it's really obvious that our friction force is in the x direction because it's literally like pointing in the negative x direction. But we also have this force of gravity that has an x component to it. It's off at an angle that's not right on the axis, and so it has an x component. The way we calculate the force of gravity is always mass times g. Mass times 9.8 meters per second squared. That's just how you do force of gravity. So when we're thinking about this as a right triangle, trying to find that that x component here, that means that the magnitude of our force of gravity is the hypotenuse of our triangle. And if you remember our SOHCAHTOA that we had talked about way back when, the sine of the angle, here's our angle, is the opposite side of our triangle over the hypotenuse. So if we don't know what that opposite side is, we rearrange that equation, sine equals opposite over hypotenuse. That becomes opposite equals hypotenuse times sine. And so our x component is the hypotenuse, the force of gravity, mg, times the sine of our angle. Does that make sense? Does that answer your question? Yes, great. Good question. Okay. Well, if you guys have any other questions, feel free to type them in the chat and I'll try to pause briefly and take a look at those. But that, I think, is the end of our example for something on a hill. And like I was just saying, if you want more practice with these types of questions, then check out Canvas later today. I'll post questions and I'll post solutions. Maybe not at the same time because I'll have to create the solutions. But they'll both be there eventually for you to check your work. Okay, air resistance. So there will be times when air resistance cannot be ignored. For example, if we're talking about terminal velocity, where something is falling as fast as it possibly can, the force of gravity pulling down is exactly equal to the air resistance holding it up, those types of things. So when air resistance can't be ignored, it just becomes a lot more complicated to calculate things. Not even just thinking about forces, but thinking about projectile motion. Figuring out the trajectory of a projectile becomes much more complicated. How far it goes, how high it goes, all of that changes when air resistance comes into play, which we know is real life, right? So much of physics 1 is not actually real life, it's just the ideal case. But the effects of air resistance depend on the velocity of the object, so the acceleration is no longer constant. And up till this point, we've been doing examples where we have constant acceleration, and we just don't have that when we're considering air resistance. So the maximum height and the range decrease, right, because the object is having to force itself through the air. Or your book says through a fluid. Air is considered a fluid in this case. So the trajectory is no longer a parabola, and the effects of this are cumulative, so they compound on each other over time. And so our blue line is our nice parabolic motion. That would be if we're ignoring air resistance, so that's what we've seen up until now. But the red line is if we are considering air resistance, and you can see there the difference in their shape. We launched it at the same time, the same force, the same angle, all that jazz. And if each dot represents like 1 second, we'll say, then you can see the effects are present after just 1 second of flying through the air. This red dot is not as far along its path as the blue dot is. So you can see in the trajectory that's having to force itself through the air. And every second, it goes less and less far compared to its ideal case blue trajectory. So we said that effects depend on velocity, and so we have to look at it kind of in two different cases. If we have a low speed, then the force of air resistance equals k times velocity. And k is a constant that depends on the shape and the size of your object, as well as the particular fluid that it's going through. So in this case, in your equation, you see this F is a lowercase f, just like we see for friction. And that's because air resistance is basically a form of friction. It's just friction due to a fluid or due to air in this case. But also when we're moving at low enough speeds, our terminal velocity, Vt, is mg divided by k, right? Mg comes from the force of gravity because at terminal velocity, the force of gravity is exactly equal to that force of air resistance. So that would be our equation for terminal velocity or terminal speed if we're moving slow enough. But if we're moving at high speeds, like raindrops falling from the sky or airplanes, of course, they're flying at high speeds, then our equation changes a little bit and becomes the force of air resistance equals capital D times B squared. So D is again a constant that depends on the size and the shape of the object, and in this case, the density of the fluid, hence D. And our terminal velocity is a little bit different now as well. It's the square root of the force of gravity, mg, divided by d. So it really depends on how fast you're moving, which is one of the reasons why it's so annoying. Okay, but this equation for terminal speed explains why heavy objects in the air tend to fall faster than light objects. Because, like, let's imagine that you have a plastic ball and a metal ball that are the same size and shape and all that stuff. They're just different masses. So if we have two objects that are the same physical size, but they have different masses, they would have the same value of D because they're both falling through the same air, but they have different values of mass. So the more massive one would have a higher terminal speed, and so it would end up falling faster, right? And that's why when we say like, oh yeah, if you drop a feather and a hammer, they fall at the same rate because gravity's pulling on them the same way. Like, yeah, that's true in a vacuum, but that's not true on Earth because of air resistance. I say on Earth, I mean like in real life, not inside a vacuum chamber. But this same idea also explains why a sheet of paper falls faster if you crumble it up into a ball than if you just let it drop flat. Because the mass is the same in this case, but the smaller size from the crumpled paper affects the surface area, and it makes your D value smaller, and so it makes your terminal velocity larger. Any questions, comments, concerns about air resistance? I'm not going to do an actual example because I don't think very many professors do air resistance in Physics 1. They save that generally for fluid mechanics and later physics classes. You're welcome, Gabriel. It was a good question. I'm glad you asked it. Okay, great. So in case you're wondering where these equations came from, they are all outlined in the textbook that I've been using, the university physics textbook that you'll almost undoubtedly have to get when you take Physics 1. But it's Calculus 2, it's integration, and I haven't taught you that because you don't use it a whole lot until Physics 2. And also it's Calculus 2, so I just didn't want to get into the nitty gritty of it. But if you have the textbook, it is there for you in section 5.3 if you want to check it out. Okay. Any last questions about Newton's laws or how to apply them before we move on to work and energy? When will this PDF be uploaded? It will be uploaded later today by dinner time, I would say. Here, dinner time. Yeah, tonight at some point. You're welcome. Okay. All right. So just a quick poll as I get our question. Okay, Colby, why is there a difference between low speeds and high speeds? Is there any kind of threshold that acts as a determinant when to use which formula? I didn't find in the textbook a specific number for a threshold. There might be one that they just didn't happen to mention. But I mean, you can feel the effects of velocity. Like next time you're in a car and you're driving, like stick your hand out the window. When you're at low speeds, you can like play with your hand a little bit in the wind, but when you're going faster, like you really feel the force of air resistance pushing back on you. I'm not sure necessarily conceptually why there's such a difference between those two. But that would be a great question for further research. Okay, so yeah, I guess you'll have to look into it. So quick survey then as I get chapter 6 all set up and ready to go. How do you guys feel about, like, what's your comfort level in chapter 5, how to apply Newton's laws in these various scenarios on a scale of 1 to 5? How do you feel? Okay. Okay, good. 4s, 5s, mostly. 3.5, probably 4.5 if you actually do the practice. Yeah, actually doing the practice does tend to help. It's crazy how that works. So I'll make sure that I put up plenty of practice for you if you decide that you would like to practice. But I mean, you will be seeing these again in your Physics 1 class whenever you happen to take it, whether that's the fall or the spring. There's another question here. Why do we have to multiply by the sine and not the cosine in example 14? That was purely based on the way that we drew our forces in our free body diagram. Let me pull that back up. Sorry, I didn't see that sooner. Okay, let's go back to example 14. So we did both, right? When we were doing the y direction, we did cosine because this y component of gravity here is the side of the triangle that's adjacent or next to our angle. And in SOHCAHTOA, ka means cosine is adjacent over hypotenuse. So whenever we're dealing with the adjacent side of the triangle, we're going to use the cosine of our angle. But when we were calculating the x direction, we used the sine because that's the opposite side of our triangle from the angle. So here's our angle, opposite our angle is the x component. So we did use both cosine and sine. It was just one we used for the x and one we used for the y, and that depended on like how we drew our particular angles. Does that make sense? Okay, good, good. I like the O's. That's a good moment from a teacher. Okay, so let me switch over then to chapter 6. Dun, dun, dun. Oops. Okay, can you guys see chapter 6? Hold on, I'm getting there. Okay, you see the kitties for chapter 6? Woo! Okay, great. Okay, so chapter 6 is about work and kinetic energy and also power. I didn't get around to finishing up the power notes because I didn't know if we would get there today. So we'll start with power tomorrow, and that will be our wrap up of chapter 6. And then we'll talk about the other types of energy also tomorrow in chapter 7. Um, but work and kinetic energy is the topic of the day. So work. We tend to get a little bit confused, I think, with the concept of work in physics because we use this word so often in everyday life, and it does not mean the same thing in everyday life that it does in physics. Not quite the same thing. So, like when you go to your job, you say you go to work. Or when you go to the gym, you say, oh, yeah, I'm going to go work out. That's not I'm not quite the same type of work that we're talking about. Working out is kind of related to work, but it's not the same thing. Okay, so work is really the energy that's added to a system by some force. And we can think about this in terms of just one force at a time or all of the forces that are acting on a particular object at that time. So the symbol for work is capital W, and we have to be careful because the symbol for weight or force of gravity is sometimes lowercase w. So just be aware of that. Also, capital W is a unit for watts, which is related to this topic as well, but not the same thing. So just be careful with that. Yeah. The units of work are newtons times meters or joules. So sometimes you'll see it Newton meters, but really a Newton meter is a joule, capital J. So the way that we calculate work, I have here two different equations, but both are helpful and valid. So work equals F dot D. That is not a times. It's not F times D. It's F dot D. And this goes back to chapter 1 when we were talking about multiplying vectors together. And I told you that there are ways to multiply vectors together. We just weren't going to talk about it then because it wasn't relevant then. Well, now it's relevant. So one of the ways that we multiply vectors together is using what's called a dot product. There's also cross products, but we're not quite there yet. So a dot product really just kind of tells us how parallel two forces are to each other. Or in other words, it's the magnitudes of those two forces multiplied together times the cosine of the angle that's between these two forces. So basically it tells you how much of your force is contributing to motion. So I have here a little car from my son. He picked it out. Picked it out especially for you guys today. So this car, okay, the motion of the car is going to tend to be forward, right? We're just going to imagine that we're driving forward. And if we push our car this way, which I guess for me is to the left, I don't know which direction is for you, but forward for the car, then all of the force that I'm pushing with this car, all of that force is contributing to its motion. If I push this car at an angle, Well, now I'm partly pushing it down onto this notebook and partially pushing it forward. So only part of the force that I'm applying is actually going towards making this car move forward. And the other part is just kind of being wasted as I push it harder into the ground. If I push the car straight down on the notebook, then none of the force that I'm applying is going to making it move forward. All of the force is going downward, not forward. So whatever amount of force is parallel to the direction of motion or the displacement, that is the force that's doing work. So this angle then, right here, between the force that I'm applying and the displacement, that is the cosine of our angle. It's kind of bizarre to think about, but hopefully as we do some of these examples, it'll make a little bit more sense. So in this equation, F is the force that's applied, or any force that we are looking at for that specific scenario. Sometimes I'll be asking, what is the work done by the normal force, or what is the work done by gravity, not just an applied force. D is the distance through which the object moves, so that's the displacement. Sometimes you'll see that written as lowercase s in your textbooks, but it still means displacement. And then theta is the angle between the direction of the force and the direction of motion. So you might notice too in this equation that F and D are bold letters, and that's because they're vectors, right? Force is a vector, displacement is a vector, direction matters for both of those things. But work is a scalar, and that's super weird because you would think if you have a vector times a vector, it would equal a vector, but it doesn't. Annoying, I know. So work is a scalar. The direction doesn't matter for work. Same thing with energy coming up in a couple of minutes. The direction of energy doesn't matter at all. And work can be positive, negative, or zero depending on the situation. It'll be positive if the force has a component that's in the same direction as the displacement. It'll be negative if the force has a component opposite to the direction of displacement, like friction, for example, is usually negative work. And it's zero if the force is perpendicular to the direction of displacement. If it's not contributing to the motion at all, the work that it is doing is zero. Okay, so you might, going back to our typical definition of work, like, oh, I work out. You might think that it's hard work to hold a barbell motionless over your head and look all like, hey, look at my muscles. But you can hold it there motionless for 5 minutes, and actually you haven't done any work at all on the barbell during those 5 minutes. There's no displacement of the barbell, so you're not doing work. Hate to break it to you. At least you're not doing work on the barbell. Your muscles are doing work on each other, and that's why you get so tired, but you're not actually doing work on the barbell. Same idea too, if you're walking across the floor and you're carrying this super heavy textbook, or in my case, carrying super heavy toddlers, then you're not actually doing any work on the book. The book has a displacement as you walk, but your force holding it up is not in the same direction as its displacement. So your force holding it up is doing zero work on that book, even though you get super tired carrying them around and around and around all day. It's just physics for you. Hate to break it to you. Okay. So I want you to give this a try, just thinking through. If you have a calculator, that's super helpful. But there's our equation for work there at the top. Force times displacement times the cosine of the angle between our force and our displacement. So you're pushing a box across the floor. Think about these cases which one would you be doing the most work? Which one would you be doing the least work? Take a couple of minutes, go through this, and we'll come back together and go through the answer. Okie dokie, let's think through this together. So in case A, when we are pushing with 30 newtons in the direction of motion, that means all of the force that we are applying is going to help this object move in that direction that it's going. So the cosine of our angle is 0, right? Because there's no difference between the direction of motion and the direction that we're pushing. So all of that 30 Newton force is going to help it make this displacement of 10 meters. So 30 times 10 times the cosine of 0, cosine of 0 is 1, gives us work of 300 joules. In case B, this 25 Newton push at an angle of 60 degrees from the direction of motion for 5 meters. Okay, here's our force, 25 newtons, our displacement of 5 meters, and this time our angle between our force and our direction of motion is 60 degrees. So that gives us 62.5 joules of work. In case C, the 10 newtons of friction for 6 meters. So 10 newtons is our force, 6 meters is our displacement. But remember, friction acts opposite the direction of motion, pretty much always. So that's 180 degrees, right? If it's moving this way and friction is pushing this way, that's a 180 degree angle between the two of them. So the cosine of 180 is -1, which gives us work of -60 joules. And if you guys remember a couple minutes ago, I had said that friction is usually negative work. It like takes energy away from the system. And then in case D, our 25 newtons of normal force, well, if our box is sliding across the floor, either direction, left or right, the normal force is perpendicular to the floor. So that normal force is not doing any work at all on our object. It's not helping the displacement at all. So that would be doing 0 joules of work. Okay. Any questions about this kind of, not conceptual, but like beginner example before we jump into some of these other examples of work? Terajoules? No, I did not say terajoules. Terajoules would be insane. Yeah, that would be a lot. We're just dealing with regular joules here. We have kilojoules in an example coming up, but we'll get there. Okay, so here's official example 1, work done by several forces. Here we go. A farmer hitches her tractor to a sled loaded with firewood and pulls it a distance of 20 meters along level ground. The total weight of the sled and the load is 14,700 newtons. The tractor exerts a constant 5,000 Newton force at an angle of 36.9 degrees above the horizontal. There is a 2,500 Newton friction force opposing the sled's motion. Find the work done by each force acting on the sled and the total work done by all the forces. Whew, that's a mouthful. So I drew, well, I didn't draw because I'm not that skilled at drawing. The textbook drew a picture for you of what's happening in this scenario. What I want you to take a second to do is draw me a free body diagram. Where are the forces? What forces are there in this situation? So take a minute and draw your free body diagram. All right, so let's take a look at these free body diagrams. So here's our object. I'm drawing in the x-axis because we do have a force acting on an angle, and I just want to have a reference point. So we have the force of gravity, or the weight, pulling down, and that's 14,700 newtons. The normal force from the ground holding it up, we don't know how big that is. Is it equal to the force of gravity in this case? Is the normal force equal to the force of gravity? No, it's not. Good job, Gabriel. It is not equal to the force of gravity. It is a little bit smaller. That's right, because we're pulling up on this load of firewood at an angle, so it's kind of like you lifting while you're pulling. The ground doesn't have to hold it up quite as hard as it would if it was just resting on the ground. So the normal force is not equal to the force of gravity, but we don't know how big it is right now. We also have this force of tension. I called it a tension because there's a chain here holding them together. If we called it an applied force, that's fine too. But we do know that this is 5,000 newtons. It's given to us right there. And we know the angle is that 36.9 degree angle. And lastly, we have friction opposing the direction that it's moving. So that would be 2,500 newtons of friction force. So this is our free body diagram. And I drew all of the forces different colors because they are not all the same size. But we don't really know how big the normal force is, but we know it's not the same as the force of gravity. Okie dokie. So to start thinking through this scenario then, the weight is perpendicular to our displacement, right? Our displacement is going to be, in the case of our free body diagram here, to the right. The tractor's pulling it to the right. So that force is perpendicular. The work done by that force is 0. The normal force is also perpendicular to its displacement. So the work done by the normal force is 0 in both of those cases. The tension force, that is not perpendicular to our displacement. There is some amount of that tension force that's being applied by the tractor that's making the firewood move to the side. So the work done by tension, WT, equals the force of tension times the displacement times the cosine of our angle. We know here it's pulling at a distance of 20 meters, so that's our displacement. Right? Our force of tension is 5,000 times our displacement times the cosine of our angle, which gives us 80,000 joules or 80 kilojoules. I just don't like typing all those zeros, so I left it in kilojoules. And then friction also has a component that's in the direction of motion. It's actually opposite the direction of motion, as we know friction always does. Friction is like an unruly teenager. It just always opposes everything. But the work done by friction is the force of friction times the displacement times the cosine of our angle. So the force of friction is 2,500. Our displacement is 20 meters. And then our angle from the direction of motion is a full 180 degrees, right? Because it's moving to the right, but friction is to the left. That's a full 180 degrees. So that gives us a work of negative 70,000 joules or negative 70 kilojoules. So that's kind of the answers to the first part of the question. Find the work done by each force acting on the sled. Now we need to find the total work done by all the forces. And that's super simple now. All we have to do is add them all together. So the work done by the force of gravity or the weight, plus the work done by the normal force, plus the work done by the tension, plus the work done by the friction. All of those things added together gives us a total work of 10 kilojoules. Remember, we can add together X and Y components here because the direction does not matter for work. Force, it does matter, right? Direction matters for force because force is a vector. But work is not a vector, it's a scalar, so we can treat all of our directions exactly the same. Okay, so 10 kilojoules is our total work done by all of these forces. Any questions about this? Can you sum all the forces and then get the work from that? Give it a try and see if that gives you the same answer. Wink, wink, nudge, nudge. Keep in mind, though, as you do that, Gabriel, that when we're thinking about forces, the direction matters, right? So we can't just combine X and Y. We have to think about like net force in the X direction and net force in the Y direction. See if that gets you the same thing. Okie dokie. So work and speed are related to each other. The total work, as we've already discussed, the total work done on a body by an external force is related to its displacement or its change in position, but it's also related to the object's change in speed because it's related to force. And remember, force is mass times acceleration, and acceleration is change in velocity, which is speed with a certain direction. So the speed does affect the work that is done. Well, the change in speed does. So when a particle undergoes a displacement, it will speed up if the total work is greater than 0, if the total work is positive, right? And that should make sense to us because if the total work is positive, then it's like you're pushing it in the direction that it's already moving, and so it's going to speed up. It'll slow down if the total work is negative, because that's just like friction. If you're trying to pull it backwards as it's trying to move forwards, then you're going to slow it down. And it'll maintain the same speed if your total work is 0, because you're just not doing anything to interfere with its speed at all. So since we're dealing with changes in speed now, this will relate the total work done on the object to its kinetic energy. Kinetic energy is the energy something has due to its motion. And there are a couple of other definitions for kinetic energy, which we'll see play out in different scenarios coming up in a couple of minutes. But another alternative definition is the total work that was done to accelerate that object from rest to its present speed, or the total work that particle can do in the process of being brought to rest. So the symbols for kinetic energy, there are actually quite a few different symbols you might see it written as. KE is one. K is the one that the textbook uses. There's also E sub kin, or just E sub K for kinetic energy. But I'm going to tend to use just capital K most often because, again, that's what your book will use when you get university physics. So if you use something else in high school, feel free to keep using that, but just keep that straight in your head. The unit of this is joules as well, and joules is given that symbol capital J. And the equation for kinetic energy is 1/2 mv squared, where m is the mass of the object and v is the velocity. That's a really important equation to remember, so I put it in a little pink box. Kinetic energy is also a scalar quantity. Even though velocity is a vector, kinetic energy is a scalar. It depends on the mass and the speed, and it does not have a direction associated with it. Because kinetic energy can never be negative, and it's only 0 when the object is at rest. When the speed of the object is 0, that's the only time that kinetic energy is 0. All right. So thinking about, I want to just revisit these couple of definitions really quickly. So like when we think about that last definition, the total work that particle can do in the process of being brought to rest. I don't know if any of you guys are athletes or anything like that, but just imagine that you're like playing catch with some kind of ball, baseball, football, volleyball, I don't know, whatever ball you want. But this is why you pull your hand and your arm back when you catch the ball. So you throw the ball, but then also when you catch it, usually you don't just catch it like that, just moving your fingers. Usually it'll pull your arm back a little bit as well. And as the ball is coming to rest, it does an amount of work on your hand because it's exerting a force on your hand and moving it back a distance. And that's equal to the ball's initial kinetic energy. And by pulling your hand back, you're maximizing the distance over which that force is acting. And so you minimize the force on your hand. So it doesn't hurt your hand as much if you pull your hand back when you catch versus just leaving it just like that. And you might think too, like, well, what about baseball players? They tend to just like leave their hand there. Well, that's why they wear a glove, is because that glove gives them a little bit of padding, a little bit of distance for that ball to like squish into the glove when they catch it. And that also helps to minimize the force of acting on their hand. Gabriel, yep, it's a bit more tedious though. Yes, good job trying though. Okay. So that means, thinking back to this whole kinetic energy thing, that means that kinetic energy and work are related to each other. And they are through something called the work energy theorem. So this theorem tells us that the work done by the net force on a particle equals the change in that particle's kinetic energy. Here it is written out in a really important equation that you will want to have written down on an equation sheet in a test. The total work done by that, well, done on that object is equal to its change in kinetic energy. Remember that triangle symbol? Delta, that means the change in. So it's final kinetic energy minus its initial kinetic energy. Or so you might see like Kf minus Ki, final minus initial, or the kinetic energy at 0.2 minus, kinetic energy at 0.1. So when our total work is positive, the kinetic energy increases and the particle gets faster. When the total work is negative, the kinetic energy decreases and the object slows down. And when the total work is 0, the kinetic energy is constant, and so the speed is unchanged, just like we had talked about a couple minutes ago. Now, I do want to give you a little caveat about this theorem. It can only be used in an inertial reference frame. We didn't really spend any time talking about inertial reference frames yet, but those are any frame of reference where Newton's laws are true, or where it will, just where the object acts in accordance with inertia. So there are some cases where Newton's laws are not true. For example, if you're looking at an object moving near light speed, that would not be an inertial reference frame. But we'll talk about that later on. Most of these cases that we're dealing with are going to be inertial reference frames where this is true and Newton's laws are true. Okay, so here's another example. Just kind of taking what we had already done in example 1, same situation, but now let's suppose the initial speed is 2 meters per second. What is the speed of the sled after it moves that 20 meters? So I drew this additional picture up at the top there. Well, again, I didn't draw it, the book drew it for you, whatever. But here's the sled. Initially, it's moving with a velocity or a speed of 2 meters per second, and it covers a displacement of 20 meters. What is its velocity over here after it's moved 20 meters? That's what we're trying to figure out. So previously, just to recap, we calculated that the total work that was done on this sled was 10 kilojoules, or 10,000 joules. And we were given the weight in the problem to be 14,700 newtons. So from that weight, we can figure out the mass of the sled. Because remember, weight is the same thing as force of gravity, which we calculate by doing mass times g. So if we take our weight and divide it by g, that gives us the mass. So our mass of this sled is 1,500 kilograms. We'll need that in this next part of the problem. So our initial kinetic energy right here at this first point, that's pretty simple to calculate if you know the equation for kinetic energy, which we do now. kinetic energy at that first point is 1/2 mv squared, where that v is the velocity at the first point. So 1/2 our mass, there it is, 1,500 kilograms, times our initial velocity, 2 meters per second. That velocity is squared. That gives us a kinetic energy of 3,000 joules. I cannot tell you enough times, make sure you square your velocity. One of the most common mistakes that I've seen students make when calculating kinetic energy is they forget to square the velocity, or they square the whole thing, not just the velocity. Both of those are completely incorrect. We just square the velocity, but make sure you square the velocity. Do it. Do it. Okay, anyway, the final kinetic energy is a little bit trickier to find because we don't know what the final speed is. I mean, that's the whole point of this problem, is to find the final speed. Well, if we remember the work energy theorem, and we remember that the work done, the total work, is the change in the kinetic energy, well, then we can calculate it. So that means that the second kinetic energy, or the final kinetic energy, is the total work done plus our initial kinetic energy. So 3,000 joules plus the 10 kilojoules of the total work done that we found in example 1. That gives us a final kinetic energy of 13,000 joules. And so from there, now we can calculate the final velocity, or the final speed. That's the square root of 2 times the kinetic energy divided by the mass. This equation is just this equation rearranged for velocity. Right? I didn't have space to actually show me rearranging the equation, but we just took that kinetic energy equals 1/2 mv squared. We solved for v. So that gives us a final velocity of 4.2 meters per second. Okay, any questions about this example? Okie dokie. So if you have questions, of course, type them in the chat. Example 3. This also has another excessive scenario, but we'll just go through it. It has good information. In a pile driver, a steel hammerhead with a mass of 200 kilograms is lifted 3 meters above the top of a vertical I-beam being driven into the ground. The hammer is then dropped, driving the I-beam 7.4 centimeters farther into the ground. The vertical rails that guide the hammerhead exert a constant 60 Newton friction force on the hammerhead. And first of all, we want to find the speed of the hammerhead just as it hits the I-beam. Okay, so we can see that there are some important things in that scenario, but one thing that we should notice and not forget to notice is that that distance that's given to us, what units is that distance given in? Centimeters. Is that acceptable? No, it's not acceptable, right? Instead of meters, it needs to be in meters, because remember, the units for work are newtons times meters, not newtons times centimeters, and that's what gives us that unit of joules. So we have to be able to convert from 7.4 centimeters to meters. Unit conversions, chapter 1, gross. I know, Colby, I was really hoping that it was going to be a hammerhead shark as well. Maybe you can picture a hammerhead shark in your mind, just beating down on this beam, if that makes you happier about doing unit conversions. Perfect. Okay, so I just made everything smaller so I could show you the picture that your textbook has drawn for you, not me. But here's the hammerhead that is actually referring to. Feel free to replace a shark there if you would like to. But here's this hammerhead. It's falling down and it's driving this I-beam down here into the ground. So this hammerhead is 3 meters above our I-beam. And then once that hammer hits the beam, it drives it 7.4 centimeters farther down into the ground. So we are going to establish 3 key points here. Point 1 is where the hammer is all the way raised up. Point 2 is where it contacts the I-beam, and point 3 is where the I-beam settles down to. And just for the sake of time, because we're running short on it, I drew the free body diagrams. The book drew the free body diagrams in there for you. So for the hammerhead, we have its weight, or the force of gravity pulling it down, and friction from the walls opposing its motion as it falls down. So friction points up. For the hammerhead pushing on the I-beam, we again have that its weight pushing down and friction opposing its motion pointing up. And we also have the normal force from the I-beam pushing up on the hammerhead at that moment. These breaks here just go to show you that this diagram is not to scale. And we can see here that this friction force, it's not that it's like leaning off to an angle, it's just offset so that you can see that both of them are pointing upward. Okay, so let's do it. The weight of something is mass times g, so that's 200 kilograms times 9.8 meters per second squared. That's a force of 1,960 newtons downward. So our forces in the y direction, again, this is looking at point 1 up here, just initially for the hammerhead. So the sum of the forces in the y direction is the upward friction minus the downward weight, so 60 minus 1960, which gives us negative 1,900 newtons. So the total work then that's done from point 1 to point 2 is that force multiplied by the distance, and that's in the same direction, so the angle between them is 0. And the cosine of 0 is 1. So all of that work, all of that force of gravity is going to helping the thing drive down. Words are hard today. So anyway, that's our force there. Sorry, this is a typo, that should be flipped. Friction minus weight times the distance between them is negative 1,900 newtons times a distance of negative 3 meters. I'm choosing the 0 point to be at the top. So that gives us a work of 5,700 joules. At point 1, the hammerhead is at rest, so its initial kinetic energy is 0. But at point 2, it's falling down, it's moving, so its kinetic energy is not 0. Its kinetic energy at that point will be 1/2 mv at that point squared. And so that total work done is the change in kinetic energy. We know the total work done is 5,700 joules. So once we rearrange our equation to solve for velocity, like we did in the previous example, we can plug in our numbers. So velocity at that point, right before it hits the I-beam, is the square root of 2 times our total work divided by our mass, or 7.55 meters per second. Would there also be the force of tension on the hammerhead since it is suspended? That is a great point. Although we don't see in the picture what it is suspended with. But yeah, that's a really good point. I'm surprised that the textbook didn't address that. Okay, part B. Find the average force that the hammerhead exerts on the I-beam. So, as the hammerhead moves down between points 2 and 3, so driving it farther into the ground, the sum of the forces, in this case, we're looking at this picture C over here, In this case, that would be the normal force acting upward plus the friction force acting upward minus the force of gravity pulling downward. And now that I'm thinking about it, they did not include the tension force, probably because they let go of it as it's falling down. It's like not necessarily free falling, but it's not like they're um, actively holding on to the rope and trying to prevent it from falling. The whole purpose of a hammerhead is to make it fall down. So they probably like let go of the rope so that it can fall, and then they use the rope to pull it back up. So when they're pulling it back up, then it would have tension. But up until that point, we're not including tension because the rope is not actively pulling up on the hammerhead. Hopefully that answers your question. Okay. Anywho, back to this one. The total work during this displacement, this little tiny 7.4 centimeter displacement, is what we're looking at. So that's the net force times its displacement from point 2 to point 3. So its initial kinetic energy we just found to be 5,700 joules. Its final kinetic energy is 0 because at that point it's at rest once it's reached its bottom point. So the total work done on it then is the net force times its displacement, which according to the work energy theorem is the change in kinetic energy. So our normal force equals weight minus friction minus that difference in kinetic energy over displacement. So I just took this equation and I rearranged it for normal force because that would be the average force that the hammerhead exerts on the I-beam. That's what we're looking for. So our weight we found to be 1,960 newtons. Our friction force was given to us as 60. The kinetic energy at point 3 is 0 because it's at rest. It initially had 5,700 joules of kinetic energy when they contacted each other, and it drove it down a displacement of 0.074 meters, not centimeters. So that normal force is 79,000 newtons. That is quite a bit of force. Okay, any questions about this example? Okay. We'll get to this, give it a try tomorrow. We'll start off with that because we are out of time for today. But if you guys have any questions, comments, concerns, feel free to hang out after I stop the recording. And I will be happy to answer them to the best of my ability. Otherwise, I hope you have a great day and I will see you guys tomorrow.